Hello everyone, Krishna this side, and in this particular video, we will be looking into this strongly connected component. So this is actually a graphs problem, and let me explain you the problem statement and how this graph actually, how this algorithm actually works, and I'll write the code as well, walking you through the step by step. So basically, we have given an directed graph, and we need to find that how many components that are there which are strongly connected. Okay, so what does it basically means is like if we look into this particular example, okay, let me open an image which where I have drawn the same problem statement and I'll explain you guys through that. Okay, so any particular graph question that we have given, so we must have understanding about how DFS BFS algos basically works. Without understanding of that, we cannot easily solve this problem. Even the recursion is something which we need to have a strong grip upon that, then only we can solve this problem. Okay, so yeah, I hope you guys have understanding in those areas, so I'll directly explain you like how this algorithm works and what are the steps that we need to follow to get all the strongly connected components from the graph. Okay, so basically from this graph, right, the yellow circles that I have drawn, these are the different components that are connected each other. Okay, so what is strongly connected component means if I start from any point and again reach back to the same point. Okay, so if there is any cyclic formation that is available in a directed graph, so that is we simply consider that is that particular component as single component. Okay, because it is actually strongly connected. Okay, and any component that is not actually connected to this one. Okay, so let us look into this particular three as a node, right? So if we look into this particular three, even if I start from the 3, I cannot again reach back to 0, right? From 0 we are having directed to 3, right? But again from 3 I cannot reach to 0, so this is not part of this particular component, right? So from 1 if I start, I can reach again back to the 1. From 2 if I again start, I can again come back to 2. The same goes with 0. If I start from 0 and if I follow this particular path, these three components from anywhere if I start, I can easily reach back to the same component, right? So that is basically one single component. And for 3, if I start from 3 again, I can go to 4, but I cannot come back to 3. So that is 3 is actually independent component that we have. Again, if we look into the 4, this 4 is also independent because there is no directed edges from the 4 such way that we can come back to the 4. So 4 is independent component. So here in this particular example, we basically have three strongly connected components, right? So basically we just need to return 3 as an answer, right? So this is the problem statement that we have and how we can deal with this one. Okay, so basically we just have to remember only 3 steps, and if you guys get to know that those 3 steps, you guys can easily solve this problem. Okay, so what are those 3 steps, right? So first is we need to create a stack, and in the stack we need to add the element which has the finishing time. Okay, the component element which has the finishing time that we need to dump into the stack. Okay, so what I am trying to say is like if I start from the 0, right? So let's start from the 0, use the DFS algorithm to traverse through these algo components, and any element that is having the finishing time at last, that we will dump into the stack at first. Okay, so here if I start from the 0, let us suppose if we explore 3 as a node. Okay, we can start from 0 and we can go to 2 as well. There is no constraint with that, but from this particular example as I have drawn here, in the stack element, as I put 4 as at end of the stack, right? So based on that I will try to explain this. Okay, from 0, let us suppose if we explore to 3 as an adjacent node for this particular 0. From the 3 we again start exploring, we again call the DFS, we reach to the 4. From the 4 we have no any directed edges, so simply we dump 4 and we go back to the 3. Again from 3 we don't have any extra external nodes that we can traverse, so 3 we put into the stack. Again we get back to the 0. From 0, yes, we have 2 as a node, so let us explore 2. From 2 again, if we call the DFS, we reach to 0 1. And from 1 again, if we try to reach out to the 0, 0 is actually visited. So there is no any other components that are there from 1 we where we can go, right? So 1 we put it into the stack and we go back to the 2. Again we put 2 into the stack because there is no any extra other nodes that we need to explore. From 2 again we reach back to the 0, so 0 is also dumped into the stack. So this is the stack that we created with the least significant time that is there. Based on that, this stack is actually created. So why we need to create this stack? I mean, a stack is basically we again wanted to traverse from this particular nodes. Okay, we want to traverse these nodes, and the top element is having all the nodes which has started from the top priority node that is there is from where all the nodes get started. Okay, so whichever node that is having the least significant time, that will be available at the top of the stack. Okay, so basically the stack is what we have created. Again, based on the stack elements, we will try to explore these nodes and call the DFS and try to get the strongly connected components. So okay, so again I'll explain you this part. So let us now second step we will move again. So in the second step, what we basically need to do is we need to just flip these edges. Okay, from 0 to 3 there is edge, right? So from 3 to 0 we need to create the edge. From 4 to 3 we need to create the edge. From 2 to 0 we need to, so basically these whatever the edge direction that we have, we need to just flip those edges. Okay, so this is the flipped graph that we have created. And now once we create the flipped graph, right? So with this why this flipping is basically required, right? So see, even if we flip the nodes, right, from any point, even if I start from the 0 or 1 or 2, if I again call the DFS, right, I again reach back to the same node, right? Even if I flip the nodes, we are actually having this cyclic dependency still going to be remain same, right? So from the stack also, if I pick any element that is available and we try to call the DFS and explore all the nodes that are connected, we again reach back to the same node. So this way, what we get to know is like all the connected components that are having cyclic dependency, which is actually a single strongly connected component, those all nodes we simply visit them, and based on all those we visit, we will consider them as single one and we consider it as a single count. Okay, now if I now once we have this flipped nodes, we again call the DFS. Based on the stack elements, we pick the top elements from the stack and we again start exploring and calling the DFS again. And based on the flip nodes, we again explore all these nodes. Okay, and whatever the single circle that I have drawn, right, these all nodes get explored by at a single point. Okay, so based on that, we make sure to visit all those nodes, mark them as visited, so that from 3 again, if I try to explore this 0, this 0 is actually visited. So we need to maintain a visited array as well. Okay, so this way, like, we will explore all these nodes as well again, and all the components that are connected to a cyclic way, they will get explored, and this will fall under the same one. So we consider this as one, and this will be second component, and this will be third component. So based on that, we make a count and we return that count. So that's it. Like, these are three simple steps we need to follow. Let me start writing the code, and through that I'll walk you through like how things works. Okay, so here the first step, let me make sure the first step is we need to get the stack, fill the stack based on finishing time. Okay, so in this one, I need to have a stack, and the next thing is we need to maintain a visited array. Okay, so either we can maintain a boolean one or simply one. Now, okay, we don't have any count of vertices, right? So let me get the vertices, how many vertices are there. So this if we look into here, it is two-dimensional array. So in the input it is showing like this one, but actually it is array list of it is a adjacent list, right? So it is those size gets this gives us how many vertices are there, right? So because there are four vertices, at 0 we have 2 3 as its adjacent nodes, right? So from the 0 we explore 2 3, from the 1 we are actually having only 0 as adjacent node, from 2 we have only one as an adjacent node, right? So we can look into this particular example also. So based on that, like v is what we need to get. So total size of this addition is what total vertices we have. So in this visited array we need to have v size. Okay, now what next, right? So we need to fill the stack, right, based on the finishing time. Okay, so what I'll do is I'll start from the zero, because it is not mentioned that actually they are starting from the zero till the size of the list. So we will start from the zero only, and we will check that if visited of I is equals to zero. So initially, if there is nothing, the array will be having zero as by default value, and we call DFS. Okay, what we need to pass is the current element, the ADJ stack, and visited. Okay, so this will get updated time to time. Let me write the uh, DFS algo, void DFS in current. Okay, let me just copy this array list of ADJ, and then there is the stack, and then we have visited. Okay, so the DFS algo, you guys needs to have the understanding. Okay, by default, the first element that we have current, I'll make it as visited, so I'll mark it as 1. And let's start exploring the addition element that we have for 0, 2 and 3 are the addition nodes, right? So what we'll do is int adj node from this uh, adj dot get current. For this current, all the addition nodes we start in the for loop. Okay, and we now check again if, because again from the 2 we have sorry, from the 2 there is no possibility, but there could be a chance that from 4, if let us suppose if we again reach back to 3, right? From 2 we are actually having this condition, right? From 2 I explored 1, and again from 1 we are reaching to 0, right? So again 0 is already visited, so that's why it is visited. So that is something what we don't want to revisit again, right? So if visited of this adjacent node is equals 0, then only we need to call the DFS. Okay, so in the current, now this will get updated to the adjacent node. ADJ will be remain same, stack is going to same, visited is something what need to pass. And at the end, once we reach to the 4, right, now there is no direction where we need to go further, right, from the 4, right? So that is something what we need to put into the stack. So stack dot push the last node that we have. So once we push 4, we return back to the 3. Now 3, there is no any leftover elements that we need to process, so 3 will get pushed into the stack, and again it return back to the 0. So that's how things work. So in the stack we just need to push the current element that we are trying to process. Okay, so that's how the DFS algo work basically. Now the second step is we need to flip the graph, right? So what is it? Flip the adjacent graph. Okay, that we have. So how we need to do is like I'll just create another array list of adjacent one. So let's name it as adjt equals new array list. Okay, and since it is array list, so I need to fill it with all the objects that it basically requires. New array list, and here again, and as I said, like we will be processing again we need to do the DFS, and we have to have this visited thing, right? So instead of having another one, I'll just use the same one. So for that I'll just update it with 0 for now. So this is something what we maintained objects here. Now what next is I need to flip the elements, right? So basically flipping is not a big thing, right? So we need to again go from 0 to all the vertices that we have. Okay, and here what we will do is we will get the adjacent node from this what is that, adj dot get I, and we need to update this adjt dot get adj node. So in the adjacent node, now we will simply put I. Okay, so sorry, this is array list, right? So we have add as this one. Okay, this is how like we basically simply flipping it. So we are getting this addition node, and in the addition node we are just dumping that current node. Okay, simply we are flipping the nodes. Nothing complication here. Okay, now the third step is uh, just count the SCC, strongly connected component, processing the stack. Okay, so what I'll do is I'll get SCC as 0, and this is something what I need to return. So here I'll loop through the stack dot if stack is not empty, till then we are processing it. Get the top element from the stack dot pop. I'm popping the topmost element, and again let's use the same technique. See, why we are using visited is the idea is pretty much simple. We don't want to revisit the same element and fall into the TLE and all, right? So we don't want to keep on looping the same thing. So this is something we need to take care, right? So visited of current if equals 0, again called DFS2, uh, DFS2. Here I need the current, then ADJT transport of that one we need. Visited is something also what we need. So I'll just copy this one. Here we are just using same technique, but it is DFS2. There is no stack involved here, and visited is there. This is also we don't want here. DFS2 stack is also what we need to remove. Same thing, we are just doing the same DFS technique. We are just applying it, and we are doing it. And here we will do count. Okay, now this way what happens is if we look into the image, we pop the top element from the stack. From 0 we started exploring adjacent nodes in the DFS algo. 1 we reach, from 1 we reach to 2, from 2 we reach to again 0. 0 is already visited, so there is no external nodes from 2 where we need to go, so we return back to the 2. From 2 we return back to 1, from 1 we return back to the 0. Now all these are visited. Okay, now let's pop the 2. So our 2 is already visited because it has been marked as 1. So we just removed from the stack. 1 is already visited because from this 0 as we started, these all got visited, right? So 1 is also simply get removed from the stack. 3 we got popped from the stack, and from 3 there is only one edge that is moving to 0. So this 0 already visited, so there is no any extra nodes that we need to visit from the 3, right? Because there is no directed edge from the 3 apart from this one. So we are not processing anything further. So 3 is also get counted here. Okay, so the SCC that we are doing it, right? So this is like this in the first loop, all these 3 got visited and it considered as a strongly connected component, so that one SCC got updated to 1. Now from the 3, from 0 we all process this one. 2 is not getting involved because 2 is already visited, so this particular condition VIS is not coming right inside here. It is not allowing us to come inside here, and SCC is not getting updated for 2 as well as for 1. Right now, for 3, it will get updated because 3 is still not visited. So from 3, now 3 got visited using the DFS algo, and 0 is already processed, so it returns back, and SCC got updated to 2. Now 4 again from the stack it get popped, and 3 is already visited for 4, so 4 is also considered as a strongly connected independent component. So based on this the SCC get updated to 3, right? So that's it. Like so these are the 3 steps that we need to follow, and we need to make sure that let me run this one as well first. So yeah, the output, expected output is 3, and we are getting 3. So that's it, right? So these are the basically 3 steps that we need to follow to get all the strongly connected components that are there. Further, we may ask that like just get all the strongly connected components. So instead of here, we can maintain another array list, and we can keep on pushing those elements that are there in the connected components, and yeah, we can process further, right? So those are the simple steps going ahead. But yeah, this is another important algorithm that we have. So I hope you guys get this idea, like how strongly connected component algorithm actually has been done, right? So that's all from this video, and yeah, bye bye.